Okay, welcome back again. So this is the fourth part of this October 2024 Unit 4 Edexcel exam, which was the latest exam in the series. Physics, Further Mechanics, Fields and Particles for the International A-Level. And we went through the multiple choice in part 1. If you watched it and given me a thumbs up, thank you very much. If you find my videos useful, I do appreciate it when students show their support by hitting that like button. Many students are watching them and are not showing that they like the videos. And with YouTube's algorithms, unless you get a lot of followers and you share the videos with your friends, the channel doesn't grow. And this is done as a free service, so I'm not getting paid to do this. I'm doing this on top of my normal full-time job. So please comment if you find my videos useful. Any feedback is greatly appreciated. I try to do them in a low-tech way. I print the paper when I'm at work. I bring it home, and when I have time off from all other responsibilities, like just personal life as well as finishing work for my employers, I then spend some time helping you guys with preparing you for your A-levels. So if you do find them useful, please explain to me in the comments what you find useful. It doesn't take a lot of time to hit the like button. Share it with your friends. I've got students, most of my students, Bangladesh seems to be very high proportion of students watching it are from Bangladesh. I'm in the UAE, so I'm getting quite a few in the UAE and the rest of the Middle East, but I know that I've had students commenting from European countries as well. So this year I'm also starting to do linear papers for Edexcel, because I'm actually moving across from international A-level to linear. So as I said, if you find the videos useful, please give me some feedback. Hit that like button. I want to get a much more high proportion of students watching it and showing appreciation, because a lot of time goes into producing these exam papers for you. So without your help, I can't get to spread the word and get the 1,000 subscribers I need to be able to go to the next level. Okay, I hope you like the low tech. I think the low tech is useful in that I'm writing the answers out as you should, and showing you the way you can communicate and drawing your attention to the key points in each question and going through the concepts. Okay, I don't offer any other free services, so I know people are sometimes asking for me to send them the paper. I don't do that. I mean, even for myself, I don't keep a PDF copy of the papers when I'm at home. But all of that I need to do at work, so please don't ask me to send you copies of papers or mark schemes. That's not a service I have time to provide. You'll need to find another way. I know there are websites where you can download papers even though they're not the official website, but you'll have to find out from your friends, or maybe people in this channel can help you with that kind of advice. So do feel free to use the comments as a way of asking other students as well for help. All right, so thanks for that, listening to that plea. The other suggestion I have is when you're listening to it, I would listen to it at 1.5 times speed, because it'll save you time. You don't need to listen to it at the speed at which I'm talking at. Listening is quicker than talking. The diagram shows, in this question 16, some equipment used by a teacher to demonstrate the action of electric fields. Yeah? It's kind of analogous to a LINAC, and that's what they're going to go to. So you've got 1800 volts on the top line and 0 volts on the bottom line, and you've got conducting strips at regular intervals of distance, and a ball which is going to be accelerated by the voltage. Okay, so a long white plastic track has strips of conducting material, as I've just shown you. The strips on one side of the track are connected to a potential difference of 1800 volts, and the strips on the other side to a potential of 0 volts. A ball with a conducting surface can be accelerated along the track. Okay? So this is getting to the point of how does this model compare with a linear accelerator. Okay? So it says the teacher places the ball on the first strip. So you can see the ball has been placed on the first strip here. Okay? So it's at it's on the 1800 volt strip, because you can see how the top line are all connected by a circuit to the 1800 volt part of the circuit. So the teacher places the ball there. The teacher then switches on the power, yeah, and the ball accelerates. Okay. So the size of the gap between the strips is 2.0 centimeters. Now remember, you've got to change it from centimeters to meters. Now this is actually a mechanics question. It says the ball accelerates uniformly. So uniform acceleration is what we're doing across the gap between the first strip and the second strip. Okay? You don't need to think too deeply about it. They've given you time. They've given you distance. So in total, you're given this information. Okay? So you're given all that information, and you know that initially the ball was at rest. Yeah? The ball was at rest initially when it was placed on the first strip. Okay? So we know that u is 0. They want you to show, using the constant acceleration formula, yeah, or using a constant acceleration formula, s equals ut plus half at squared, they want you to show it that the ball's acceleration should come out to roughly 0.8 meters per second squared. Okay, so this is a good revision of mechanics. So once you are using s equals ut plus half at squared, where u is 0, yes, you can change the subject of the equation to make a the subject of the equation as 2s over t squared. Put the numbers in, and you'll see that the acceleration to two significant figures comes to 0.83 meters per second squared, and to one significant figures it's 0.8, which is what we were meant to prove. It is correct. Okay, so this is a good analogy to a linear accelerator, which they're going to go into in a moment. But first they want you to think about what's actually happening. Why is it behaving this way? Okay, so when placed on the first step, the ball is charged to the potential of the top row, which is 1800 volts. Okay, you've got to show that the charge on the ball is equal to 2 times 10 to the minus 9 coulombs. Okay, so will Q be equal to 2 times 10 to the minus 9 coulombs? All right, so they want you to look at electric fields. They're telling you that the radius of the ball is 0.95 centimeters. Okay, so about 1 centimeter. Now, so you've got to use V equals KQ over R, where K is equal to 1 over 4 pi epsilon naught, and always it's a good idea of using this instead of using 1 over 4 pi epsilon naught and working it out, because they've done it for you and they're giving it to you on a data sheet. 1 over 4 pi epsilon naught always comes to 8.99 times 10 to the 9. So once you know that, you know K, you know V, and you know R. The only one you don't know is Q, so you change the equation round. So you want to work out Q. There's the 1800 volts. There's the radius, V times R divided by K, the constant proportionality, will give you the charge. And it comes to 3 significant figures as 1.90. Yeah? which is to one significant figure, 2 times 10 to the minus 9. So we have shown that it is correct. Yeah? So we've answered the first part of this section. It then says there is a force on the ball. Okay? There's a force on the ball due to the field. So that's why it accelerates. Okay? So there's a uniform field between the strips. Okay? Now uniform fields, you can use this equation. E equals V over D. Now we know V is 1800. We know the distance between them. Yes? It was given, the distance between them was given in part A. Yeah? So first you use that equation to work out the field strength. So 1800 over 0.02 gives you a field strength of 90,000 volts per meter. Okay? Because it's the uniform field strength. And when you do that, you can always work it out. Once you know the electric field strength and you know the charge from before, you can use F equals QE to work out the force, because the electric force is the charge times the electric field strength. So there's the charge that we worked out before to 2 significant figures. Don't use the rounded up value. There's the electric field strength. And you can get the force as being 1.7 times 10 to the minus 4 newtons to 2 significant figures. Yeah? So most of the data is provided to 2 significant figures. So we want to find out, here it says, deduce whether this is the only force that's accelerating the ball. Well, if that is the only force that's accelerating the ball, you can use Newton's second law, yes, to see if electric force due to the field divided by the mass of the ball, which they've given to you here, is going to give you the right acceleration. And when you do that calculation, put the numbers in, you'll see that it comes out as greater than 0.8. It comes to 0.95 to 2 significant figures. So if it's 0.95, then you can just write this down. Since 0.95 is greater than 0.8, yes, there must be other forces acting to increase the acceleration from 0.8 to 0.95. Okay? Or actually, yes, the force is greater, so there must be forces acting against the field. That's how I should have put it. So excuse the way I explained that last bit, because your acceleration is higher than the 0.8 that we wanted to work out here. Okay? So that's your conclusion, and that's the final mark that you get for this part of the question. Okay? Hope that makes sense. Part B, now this is where they want to use this as an analogy, this model for a LINAC. Okay? So this equipment can be used as a model, it says, to demonstrate the acceleration of charged particles in a LINAC. Okay, when placed on the first strip, the ball is charged to a potential of 1800 volts. Okay, that's the only time it gets a charge, when it's on the 1800 volt strips. The ball then accelerates towards the next strip, which is at 0 volts. Remember, if something is charged, it will go from high voltage to low voltage, where it will then discharge because it's gone to 0 volts. But in that process of accelerating, it will have momentum, so it will keep moving. Don't forget that. Okay, that's Newton's first law. But then moves at a constant speed towards the next 1800 volt strip, 1800 volt strip. Yeah? The ball is then charged again and accelerates again to the 0 volts, and this process repeats itself. The pattern of movement continues until the ball reaches the end of the track. Okay, so it's a repeated process. The diagram shows part of the model here, and they want you to pay particular attention to the shaded area, xy. All right. It says the shaded area, the shaded section between x and y corresponds to the drift tube in a LINAC. Okay? So it corresponds to the drift tube in the LINAC. Yeah? Give one similarity and two differences. So they want one similarity and two differences in the way this section, so the shaded area of the model works, and the way a drift tube in a LINAC works. Okay, so here I've first done the similarity. In the model, yeah, in the model, the shaded area, in the shaded area of the model, the ball must move at constant speed. Yeah? Well, this is a similarity, because with the speed within a LINAC, the drift tubes, yes, in the drift tube, they also move at constant speed. So that's the only similarity. And then what are the differences? The differences then are, in the model, the lengths of the sections are constant. Yeah? Whereas in a drift tube, the drift tubes, in the LINAC, the drift tubes increase in length. Yes? So in the LINAC, the accelerated particles are charged. Yes? But the ball here in the model has no charge in the shaded area. Yeah? Because the shaded area is just gone through the 0 volts. So that's the two differences that I wanted to focus on. Now, if you actually eventually do see the mark scheme, I haven't got the mark scheme in this PDF. If you do see the mark scheme, you will notice alternative points. Okay? And if you can see the alternative points, or you can make alternative points, these are not the only differences you could note. For example, the time spent in the drift tubes is constant. Yeah? And you have to think, is the time spent in the shaded areas constant? Yeah? Or is the ball continuously speeding up, and therefore it won't be a constant time in the shaded areas? Yeah? There's a no field in the drift tubes. The field is only between the drift tubes in a LINAC. Whereas in this model, there's electric fields all the time. Yeah? So it's a good way of thinking. Models are a great way of thinking, but models are not always correct. They're just sometimes useful. And I think that's a very good way of remembering that models are not always correct. They're just used to give you a better understanding of how things work and how to think about things. And then the final part of this question, it says in the model, and this is now a continuation of the differences between them. In the model, the lengths corresponding to the drift tubes, yeah, are constant. Yeah? In the model. But explain why the lengths of the drift tubes in LINAC are not constant. Okay, so in other words, they want you to now explain what you know about linear accelerators. And this is such a common question in Unit 4. So in a LINAC, you've got to now explain what's happening. The time spent by the particles in each drift tube must be constant. Why? Because it needs to match the period of the AC power supply. And you want it, as soon as it leaves a drift tube, you want the drift tube in front of it to attract the charged particle that's being accelerated. And if you don't get the time spent in the drift tube correct, then when it comes out, it will not be synchronized with the frequency of the AC electricity. But since the particles accelerate, yeah, between the drift tubes, they travel further in the same unit of time. So the next time they go into the next drift tube, they'll be moving faster, in other words. And because they're moving faster, they're going to travel further in that cycle of the AC. So the drift tubes must be designed to increase in length, so to synchronize with the frequency of the supply, yes? Or you could say to synchronize with the period of the supply. So as soon as they exit the drift tube, the AC power supply will make sure that the drift tube in front of the charged particle will be the correct polarity to increase, to accelerate the electrons. Okay, so this you can see is a complicated question in that it's 14 marks. So I'm going to make that a standalone YouTube video, and I'll come back and do question 17 in the next video. So again, sorry for nagging you about liking and showing your appreciation, but I think it's just a matter of courtesy when someone has spent time producing these videos for you, that you can show the support, yeah? And then that's all the enticement I need to be able to carry on doing these videos for you, okay? Because really I'm making these videos for my own students so that they can go and work beyond the lesson and hopefully get them higher grades, and you're getting it for as part of the deal. Okay, so the next question is going to be on circular motion, and it analyzes again mathematically what's happening. So we'll come back to this in the next video. So thanks for watching, and see you in the next video. Bye for now.